Manufacturers make absolute claims all the time. A factory might guarantee that their machines produce perfectly identical candy bars, each weighing exactly 5 grams. But the physical world is messy. If you pull a random sample of 50 bars and put them on a scale, your average will likely be slightly off. You might get 5.1 grams. The question is the factory's claim false, or are you just seeing the normal, random variation of the manufacturing process? We need a way to mathematically distinguish between a meaningless random fluke and a verifiable fact. Take a look at this official record from the Power Scaling Bureau. They claim Kaido, the Flame Fist, has a power level of exactly 100. To test this, we simulated 11 battles, yielding a running average of 100.9. That's higher than the official claim, but we only ran 11 battles. Is that tiny bump enough evidence to call the Bureau a liar and bust their claim? We can't answer that with just a gut feeling. We have to use statistical hypothesis testing. Every statistical test operates like a legal trial, built on the rule that the defendant is innocent until proven guilty. We start with the null hypothesis, the default assumption that the status quo is true, and there is nothing interesting going on in the data. For Kaido's trial, the null hypothesis assumes his true power level is exactly 100. Any slight variation we see in our sample is just background noise. On the other side of the courtroom is the prosecution's charge, known as the alternative hypothesis. This is the claim we are actually trying to investigate, that Kaido's power level is definitively not 100. Here is the trick to this entire system. The math isn't designed to directly prove the alternative hypothesis. It is designed to gather enough evidence to destroy the null hypothesis beyond a reasonable doubt. This normal distribution curve shows what we should expect to happen. If Kaido's true power is exactly 100 and we run 11 simulated battles, the results should scatter right around that center point. By mapping our sample average of 100.9 onto this curve, we can calculate the exact odds of getting a result that high by pure random luck. That probability is the p-value. Before we even look at that probability, we have to set a standard for our evidence. This is the alpha threshold. Usually set at 5%, it is a strict mathematical line in the sand that determines exactly how much doubt we are willing to tolerate. Look at the bottom of the official record for Kaido's 11-battle sample. The p-value for that 100.9 average is above our 5% threshold. It was highly likely to happen by chance, so we failed to reject the null hypothesis. Now look at this new curve. What if we force Kaido to win 50 battles, and he averaged a massive 130? That shrinks the p-value to near zero. It completely breaks the status quo model, destroying the null hypothesis. To meet the burden of proof, your sample data has to be so extreme that it becomes mathematically improbable under the default assumptions. Because we are relying on a limited sample of data and not measuring every single event in the universe, hypothesis testing never proves anything with 100% certainty. We can always be wrong. If we bust Kaido's claim, but his true power actually was exactly 100, we've just convicted an innocent man. Statistically, this is a false positive, or a type 1 error. This chart of two overlapping realities illustrates the opposite problem. If we confirm Kaido's claim, because our sample was weak that day, but his true power was actually much higher, we've committed a false negative, or a type 2 error. Every test forces a trade-off. If you demand a brutal threshold to avoid a false positive, you inherently increase your risk of a false negative. P-values and alpha thresholds are not magic formulas. They do not grant us absolute, universal truths about the world. Hypothesis testing is simply a rigorous system for managing risk. It gives us a mathematical foundation to draw lines in the sand, make binary decisions, and know exactly how confident we should be in a very noisy world.